Hello, my name is John Lee, and I'm the president of Alpha Training and Consulting, and I have a true passion for helping students prepare for ASQ certification exams. However, today we're going to go over practice exam questions for the ASQ CQPA exam, and we're going to take those questions out of the CQPA primer, which is published and distributed by Quality Council of Indiana. And they have given me permission to use those questions for this video. So thank you very much, Indiana Quality Council. We greatly appreciate it. And we use this primer in our online class also. What we do is we have you go through all our lectures and exams, and you review the primer, and we go over these questions at the end of each chapter. Now, in this video, we're just going to go over 1-2 questions from each chapter, but in our class, of course, we go over all the questions. All right, if you are interested in taking a certification prep class, please go to ASQCQPA.com. That's my website dedicated specifically to the CQPA prep class, and you'll be able to learn what we offer there. And we also have many questions that are answered on that website concerning the CQPA exam. So hopefully you'll check that out. But for right now, let's go ahead and move forward and look over those exam questions. All right, question 1. Which of the following is the best reason for a product quality audit? Well, they'll test on product quality audits. First thing you need to know about product quality audits, they're usually smaller sample sizes. And you just go through with a microscope, if you will, and you look at every single thing. So it's very thorough, small sample size, very thorough, and you perform the audit just before you ship it out to the customer, so you can look for packaging issues and all those types of things. And it's done from the perspective of the customer. You must remember that also. So I don't know what this question is going to give us, but just so you know, if you understand those 4 elements or so, you're going to do just fine on product quality audit questions. So which of the following is the best reason for a product quality audit? To identify hardware deficiencies? Well, it could be, but maybe this product doesn't have hardware. So this is way too specific for that question. To initiate corrective action? Could be. For disciplinary control? No. ASQ doesn't like that punishing people. So C is most certainly out of there. To assess product or service quality? To assess product or service quality, huh? Yes. To assess product or service quality, that's the best answer. The only other one was to initiate corrective action. But what if everything's just fine? Then that wouldn't apply, would it? So the best answer for this one is definitely D, to assess product and service quality. Let's move on to question 2. The limitations of a quality cost system include which of the following items? So it's a limitation. It's looking for something negative. It aligns quality and company goals. That's not real negative, but it may not be the correct answer either. I don't know that quality cost systems aligns quality with company goals. Well, it could help because you have costs there. So that's probably true. And this is looking for a negative, so it's probably not A. B, it provides a prioritization system for the allocation of resources. Yes, it does, because you can see where all your costs are at, and you can create projects to reduce those costs. So B is definitely a good thing, and it's looking for a negative, so it's not going to be B. It doesn't resolve specific quality problems. No, it doesn't. These tools or these methodologies do not solve problems. Human beings, they solve problems, okay? So it doesn't resolve problems. You have to have a person to resolve problems. So C is most likely the correct answer. It provides a manageable overview of quality. Yes, it does. So no doubt, 2.2, the correct answer is C. Let's move on to question 3. Many training instructors have developed approaches to emphasize multiple sense learning, which is a very good idea. Which of the following options would be generally recognized to best promote student retention? Reading and hearing, hearing and seeing and speaking, and reading and seeing. No, the correct answer is reading and speaking, especially if they're speaking, such as teaching the material. You'll never learn something better than when you actually go teach it. And so the correct answer here, no doubt, is C. 3.2, teamwork benefits individual team members by offering chances to share ideas and be creative. Yes, that's a good answer. Providing the opportunity to forge stronger relationships with management. Maybe, maybe not. Maybe they don't really deal with management on a given team. So that's a little too specific. A is much better than B. Offering opportunities to implement widely held beliefs. Not necessarily, because as you learn more, you may find out your widely held beliefs are incorrect and you may have to modify them a bit. You have to be flexible when solving problems. D, giving time off from day-to-day operations. Well, that is kind of fun if you're the one on the team, gives you a break perhaps. But the correct answer here and the best answer is answer A. All right, here we are on question 9. Which two actions would most likely result in breakthrough improvement? Breakthrough improvement is very aggressive. That's what breakthrough means. So which one of these is most aggressive? Re-engineering. Re-engineering is most aggressive. And right behind them is probably Six Sigma. So A, no doubt, is going to be correct. Kaizen, Kaizen Blitz. No, they're not breakthrough. They're very small, usually simpler problems. And ergonomic design, no. PDCA, Plan, Do, Check, Act, and mistake proofing, Pokeyoke. No, those are all good, but the most aggressive is definitely A. Concurrent engineering and Kaizen, no, no doubt. Re-engineering is where you say, okay, we're just going to wipe out everything on the shop floor, we're going to paint the floor, and we're going to start over from scratch using all new technology, blah, blah, blah. And so it's very aggressive. It's wipe everything out and start over. Very, very aggressive. So keep that in mind. You'll no doubt get tested on that on the ASQ exam. Correct answer is A. All right, here we are at question 10. Using Six Sigma methodologies, a company at 4.5 sigmas would have a failure rate of what? Okay, well, the Six Sigma methodology here is a very important term in this question. It means this 4.5 sigma, you're to assume a 1.5 sigma shift. Let's go to the whiteboard and work our way through this problem. All right, here we are at the whiteboard, and this is where we start out. It's a 4.5 sigma process, as they said, which means from the average to the upper spec limit, it's 4.5 sigmas. Now, with the Six Sigma methodology, it means you use the 1.5 sigma shift assumption, which means what? It assumes this average shifts by 1.5 sigmas, because the average does move around, and so you have to consider that. And the most standard boundaries for it to move around in is plus minus 1.5 sigma, which comes from the Six Sigma methodology. So if this was 4.5 sigma, but this average moved over 1.5, then it's going to be 4.5 sigmas minus 1.5 sigmas. And 4.5 minus 1.5 is what? 3 sigmas. So this is what we want to look up after the sigma shift. We want to look that up in the Z statistic. So we'll look up 3 sigma in the Z table and find out what the correct answer is here. Let's go to the Z table. All right, so here we are at the Z table, and we're looking for 3. Remember, it was 4.5, but we had to subtract 1.5 from it, which left 3. So we're going to come down here till we find 3. That's 1.5, so I'm going to have to move the table up a little bit. So let's move that up to 3. There's 3 right there. And it's 3.00. And this would be 3.01 and 3.02 and 3.03 and 3.04 and 3.05. And it goes over, clear over to 3.09, and you come back to 3.10, etc., etc. But this one for 3.00 is 0.00135. Now, whatever you multiply this number by, it's parts per. So if I multiply 0.00135 by 100, it'll be 0.135 parts per 100, or percentage is parts per 100. If you multiply by 1,000,000, it'll be parts per million. To get parts per million, I'll move the decimal point over 6 places. 1, 2, 3, 4, 5, 6. So it'd be 1,350 parts per million. So let's go back to the blue pages and see if we can find that as one of the options for a correct answer. So here we are at question 10, and you'll notice there's my 1,350 parts per million, which is the correct answer for question 10. All right, here we are at question 6. Suppose that 5 bad electron tubes get mixed up with 8 good tubes. If 2 tubes are drawn simultaneously, what is the probability that both are good? So the probability of getting one good one, the first good one, would be, notice the sample size, you have 5 good, 8 good, 5 bad. That means there's a total of 13. So your first try, the probability is going to be 8 out of 13. Okay? But now you picked a good one, so the next trial is going to be 7 good tubes left out of 12. And you want to know the probability of getting a good one on the first try and the second try. We assume independence. So we'd multiply those two together. But let's go ahead and go to the whiteboard and work this one out. All right, here we are at the whiteboard. And so the first one you take out, the odds of getting a good one, there were 8 good ones, 5 bad ones, remember. So 8 plus 5 is 13 total. So the probability of getting a good one on the first draw there is 8 out of 13. Now you picked a good one. And so now this will become 7, and of course this will become 12. And you want to know the probability of getting a good one on the first try and the second. So it's a simple probability. You multiply those two together. It's an and statement. It's independent. So let's go ahead and do that in the calculator. Here we go, 8. Then we're going to pick ABC to put the fraction in there. 13. So 8 out of 13 times 7 out of 12. 7, ABC 12. And you just go equals. And the correct answer is 14 out of 39 is the correct answer. Let's go back to the blue pages and make sure that's an option. All right, here we are back at the blue pages, and sure enough, there it is, 14 out of 39, and that is the correct answer. It's not unusual you'll get one like this on the exam. You may be able to solve it using the hypergeometric formula also, but it's not very user-friendly, so I usually do it the way I just showed you. Here we are at question 14. A process is turning out end items that have defects of type A or type B or both. If the probability of a type A defect is 0.1 and of type B is 0.2, the probability that an end item will have no defect is. So I'm going to find out the probability of A or B being bad, and then I'll subtract it from 1, and that should give me the probability of no defect. So let's go to the whiteboard and work this one out. All right, here we are at the whiteboard, and notice I have my formula up here. Remember, this is an or statement, so it's either this formula or you just add them together. But this, if you add them together only if they're mutually exclusive, and this one said A or B or both. Both means it's not mutually exclusive. So we know we have to use this formula here. And here's the probabilities given in the problem. Probability of A is 0.1, probability of B is 0.2. So I plugged the numbers into the formula. Now we just need to plug it into the calculator. So let's go 0.1 plus 0.2 equals 0.3. So I can put that in there. 0.3. Now I need to multiply them together. So it's 0.1 times 0.2 equals 0.02. And that gives me, plug that back in, 0.3 minus 0.02. That gives me 0.28. So the probability of getting one or more bad, is that what it asks? Let me check and make sure again. Process turning out end items that have defects of type A or type B or both. Yeah. So that's the probability of type A or type B defect or both is 0.28. But they want to know the probability of success. So we're going to take 1 minus 0.28. So 0.28 is the probability of getting the defect. So 1 minus 0.28 will be the probability of having 0 defects. So let's do that. 1 minus 0.28. That gives me 0.72. And there it is. And let's go back to the blue pages and make sure that's an option. So here we are back at the blue pages, and sure enough, there's the correct answer right there, 0.72. All right, 616, a batch is known to contain 1% defectives. What is a defective? Defective means you violated a spec limit, you created a bad part. And when you say defectives, you should think about the binomial distribution. Now, if it was defects, you should think about flaws, and that goes with the Poisson distribution. Now, defectives could be binomial or hypergeometric. It just depends on the population size. What you're really looking at, if odds change, you use hypergeometric. If odds don't change, you use binomial. So hypergeometric is for small populations, relatively large sample size, and sampling is without replacement, is what they're talking about here. But this is most likely going to be binomial. A sample size of 50 is selected and the batch is accepted if one or fewer defects are found. What is the probability of the batch being rejected? Well, bad news here. We can do defective problems very easily if the sample size is 10 or less because we have the binomial tables. But in this case, it's over 10, so we're going to have to use the mathematical formula. However, I'm glad they gave us one of these so we can check it out. So first we're going to do the probability of getting 1 and the probability of getting 0. Then we're going to add those probabilities together, and that will be the probability of accepting the lot. Because we accept it if you get 1 or 0, but if it's over 1, we reject it. But look, the question asks, what is the probability of the batch being rejected? So once we calculate this, we're going to have to subtract from 1 to get the correct answer. Well, to do this one, we're definitely going to have to go to the whiteboard. So let's get over there and start working on this problem. All right, here we are at the whiteboard. This is the formula for the binomial distribution. And let me see, what page is that? See if I can get you a page, because I want you to look that up, make sure you can find it. It's chapter 6, page 6, at least in the revision I'm using. So page 6, be sure and go and look this formula up. Make sure it's tabbed so you can get to it quickly. Or make sure it's in your formula pages, because you're probably going to need it. Now, this means combination. The formula for combination is n factorial divided by r factorial times n minus r factorial. We don't need to use this formula because we have a function on our calculator to do it. But I just wanted to let you know this here, this formula here, is the expansion of that symbol. Okay, sometimes they test on that. They'll say, what is the expansion of the symbol? And the formula written out is the expansion of that symbol. Okay, with that being said, let's get to work. I'm going to erase this so I have room to write on this one. And here we go. We have to run this formula through 2 iterations. We have to run it with r equaling 1, and we have to run it again with r equaling 0. So when we run 1, r equals 1 through here, it'll give us the probability of getting at least one bad part. When we put 0 in the formula, it'll give us the probability of 0. Once we get those two numbers, we'll add them together, and that will be the probability of accepting the lot. Okay, so let's get started. First we'll do the combination with 1 here. And clear it. Okay, so in your calculator, right above the 8 button is the combination function, right above the 9 is permutation. This obviously isn't permutation, it's combination. So we're going to use second function 8. And notice what it says there. It says NCR. That's the way you put it in the calculator. First you put the sample size, then you hit second function 8 for the combination function, and then you enter R, and then you hit equals. So you enter it just like it says there. So let's begin by entering our sample size of 50. There it is. And then we'll hit second function 8. So now we did the combination, and r equals 1. So I'm going to go 1 and equals, and that's 50. So the combination is 50, which is a good thing. P to the r value, proportion, is 0.01. 0.01 to the r power, okay, to the 1 power, oops, I didn't enter it first, so I'm going to do it again. 0.01, which is the proportion defective. Remember, they gave us percentage, so we had to divide that by 100 to make it a proportion. These formulas all use proportions, not percentages. So I entered that. Now I'm going to hit y to the x. I got a little bit ahead of myself the first time. Y to the x, and then I'm going to enter the exponent, r, which is 1. And I know some of you said, I don't need a calculator to do that, but some people do need it, so I'm going to use the calculator for pretty much everything. And so it's 0.01. P to the r power is 0.01. Then 1 minus p is 1 minus 0.01. 1 minus p is 0.99. And n minus r, n is 50, and r in this case is 1, so it's going to be 49. So I'm going to go 0.99, that's already in my calculator, so I just have to hit y to the x, and it's to the 49th power, equals, and it's 0.611. So we can go ahead and put that in here, 0.611. There we go. And then just a matter of plugging the numbers. 0.611 times 0.01 equals times 50 equals, okay, 0.3055. .3056. Okay, very good. Now we need to do that same iteration with r equaling 0. This is the probability of getting 1 under those situations. Now let's go ahead and do the next one for 0. So now we're going to put, wherever r is, we're going to put 0. So let's get started. Enter the sample size, which is 50. Second function, 8. Then r is 0 this time. So enter 0 equals, and that gives you the value of the combination, which is 1. Very good. Now we're going to go p to the r value, and that's 0.01, y to the x, r, remember, 0 equals 1. So that's pretty easy. We've got 2 ones. Times 1 minus p, which is 0.99. We calculated that last time. To the power of n minus r, which is 50 minus 0, which will be 50. Now I should be able to go ahead and do that. 0.99 y to the x, 50 equals. And that gives me an answer of 0.605. Okay. Now I'm going to add those two together because we need to know the probability of getting a 0 or a 1, so that's just simple addition there. .9106. Okay, very good. Now this is the probability of accepting the lot. That was not the question, however. They asked for the probability of rejecting the lot, so we're going to have to subtract this number from 1. So let's do that. The correct answer, the probability of rejection, is going to be 1 minus 0.9106. By the way, when you subtract a number from 1, it's called the complement of. So, just so you know. So 1 minus 0.9106 equals 0.0894. Which of course is very close to just 0.9, which I suspect the answer is going to be on the blue sheets. Let's go back to the blue sheet and check this out, make sure it's correct. All right, here we are back at the blue pages. And there it is, right there, 0.090 is the correct answer. So that's not too bad. It is kind of time consuming, And I know many of you are going to struggle with this one, but my suggestion is keep practicing it, practicing it. You may have to do it 4 or 5 times before you finally get it. But please do what it takes to understand this one. It's the most difficult one we've had in this chapter, and my guess is it will be the most difficult one in this chapter. So, but please understand it, because you're probably going to see it on the certification exam. Not many of them, but if you have one, I'd like you to get that right. And because most students that fail the certification exam that take my class, it's usually by 1 or 2. So we need to take these seriously. All right, 617, a measurement that is accurate would demonstrate precision? No. Remember, accuracy is a lack of bias, and bias is the distance from the average of the measured values to the true value or acceptable reference value, to be more correct. Okay, so lack of bias, yes, lack of bias goes with accuracy. We know repeatability is equipment standard deviation. Stability is lack of bias over time, but this is talking about accuracy, so it's going to be lack of bias. 617 is no doubt B. All right, we're going to do 10 at a time on this one. We're going to do all the questions in Chapter 7, but just 10 at a time. And then, of course, I would recommend you listen to those 10 when the lecture's over with. Go and try to work them yourselves. Take good notes as you're listening to this, please. But the goal is you can do at least 80% of these on your own. 100% would be even better. Okay. All right, a process which is in statistical control. Remember what in control means? It means predictable. To be objective, you need to have a predictable process, and it must be measurable. So a process which is in statistical control will produce product specification. No, that is capability. Remember, capability is the probability of meeting spec. Okay? You could do it in CPK units, you could do it in Z units, whatever. Consistently produced product, which when it charted will fall within statistical control limits. Yes, that would represent something that's in control. So it will probably be the correct answer. Result in a CP value of 1 or better? No, that's 1. CP of 1, if the process is centered, will be a 3 sigma process. Okay, but that's capability. Remember, it's the probability of meeting specs. Produce a product which will satisfy the customer? No, that's capability to the standard of the customer. So no, the only one here that has anything to do with predictability is B. So that will be the correct answer. Here we are on question 15. If a sample size of 16 yields an average of 12, okay, average of 12, and standard deviation of 3, estimate the 95% confidence interval for the population. Assume a normal distribution. Okay, very good. So they're going to have us do a confidence interval. Now, just so you know, it's taken me a while to accept this, but whenever they say confidence interval in an ASQ exam, they mean a confidence interval of the averages, because confidence interval, by the very definition, means confidence interval of the averages. If they said point estimate, that would be a confidence interval of single events, which they don't do very often. So this one, to me, it sounds like confidence interval of the population would be the confidence interval of single events. It's not. It's the confidence interval of averages. So you have to use that formula. Now, students struggle with this confidence interval stuff, so if you need to go back and listen to the confidence interval module. Most of you will have to do that. It's not overly long, but it's very important, and it's one students just struggle with. So you're going to have to maybe listen to it more than once. So you decide, but if you struggle with this, after listening to this, you may need to go listen to that module again. All right, we're going to have to go to the whiteboard to solve this one. Notice there's no repeats on the upper control limit side, so I'm just going to calculate upper control limit. I meant upper confidence interval, and we're going to just need to do that. We'll come back and check to see which one's correct. Let's go on to the whiteboard. All right, here we are at the whiteboard. Notice I wrote down all the things that we know in this question. That's how you should start these math problems. As soon as you realize it's a number crunching problem, write down everything that you know. So we know the sample size is 16. And so that's under 30. We'd use Z if it was 30 or greater, but since it's under 30, we're going to use T. The average is 12. The standard deviation is 3. And it's 95%. And it's a two-tailed test, 95% confidence. So what is T going to be? That's what we need to look up first. So let's go to the primer and look at the T table. All right, here we are back at the primer in the T distribution. This is in the appendix. It's right by the Z table, by the way. And we want to do a 2.5% alpha risk. Why? We wanted a 95% confidence, so that leaves 5%. So you may say, well, why don't we look up 5%? Because these confidence intervals are always two tails, so you have to break up the risk. 2.5% above the upper confidence interval, 2.5% below the lower confidence interval. They're always two-tailed. So we use this column, and there was sample size of 16. But remember the degrees of freedom, which this is degrees of freedom, it's n minus 1. So we go 16 minus 1 gives us 15, takes us over to this value of 2.131. So let's go back to the whiteboard and write that down. All right, here we are back at the whiteboard. Notice I wrote the value of the T statistic in there. Now we have everything we need. And what is it going to be? This is the formula. The confidence interval is average plus and minus T times the standard deviation over the square root of n. This is the formula. Now, if you don't know where that came from, that's okay. Make sure you look it up. And you can find it in your instructor notes. You should have that in your formula page somewhere. And you may have to write that in. If you need to write that down, I left a couple pages there with blank pages where you can write formulas in. If you can't find it, write it in there. Now, obviously, you can also look it up in the primer. And the primer's nice in that it has an example problem. Page 46 of Chapter 7 from the revision I'm working from. So anyway, make sure you know where to find this formula so when you're in the test you can put it to use. Now, why do I say plus and minus? Because I'll go plus this T times standard deviation of averages for the upper control limit or upper confidence interval, and I'll subtract that to get my lower confidence interval. So I just shortened it down. Instead of writing two formulas, I just put plus minus there. Okay, but we're just going to do what? We're just going to do the upper confidence interval because there is no repeats on it, so that'll save us some time. So I can actually get rid of that minus because we're just going to do the plus. Now let's enter the data. First, of course, the average is 12. And the T statistic is 2.131. Okay. And the standard deviation is 3. So let's put that in there where it belongs. And of course the sample size is 16. So let's put that in there. And there we go. Now we just have to do the math. Do parentheses first. So 16, let's get our calculator out. I know some of you can do this in your head, and that's okay. But I'm going to put 16, and then I'm going to hit the square root button right there. And that gives me 4. So this denominator here is 4, so we can get that taken care of. And then, of course, 3/4. 3 divided by 4 equals 0.75. So I'm going to make that 0.75 in that parenthesis. So now I've simplified that down as far as I can. Now I'm going to go times T, which is 2.131, times 2.131 equals, and that makes this whole T times standard deviation of averages equal to 1.598. There we go. And then I just need to add that to 12 plus 12 equals, and it's 13.598. 13.598. And what is that a value of? That is of the upper confidence interval. So there we go. Let's go back to the blue pages and make sure this is an option and that it is correct. Here we are back at the blue pages, and notice there it is, 13.6. All right, 8.9, the organization's customer service program can be enhanced in many ways. This is true. One of the ways would be to So they're looking to enhance it, so they're looking for a positive. Provide better procedures for customer service personnel. Yeah, but you have to leave the procedures sometimes and just go help the customer. So A is good, but I think we'll find something better. Restrict access to customer data. No, that's a negative. We're trying to enhance things. We're not going to hide information. Have supervisors available to answer more questions. I don't know. Maybe, maybe not. But this D is definitely the correct one. Utilize employee involvement. Get people involved, then they have ownership to keep the customer happy. 8.9 is no doubt D. You can't do much better in ASQ question when they're looking for something positive than to put down utilize employee involvement. All right, let's move on to question 10. Here we are in question 10. A pre-award evaluation of a supplier's quality system capability should include consideration of what? Okay, pre-award evaluation. Okay, so you're just about to award them a contract, but you're doing one more evaluation. The supplier's quality product history. Yes, that's the correct answer. And it's you need to remember that because ASQ considers past performance to be the best indicator of future performance. So I knew the correct answer would talk about their past performance. A does, and it's most likely correct. B, supplier's geographical location, cost structure, future audit requirements. No. Remember, the historical performance is the best indicator of future performance on an ASQ exam. And I think that's true. I really do. All right, here we are in question 6. Which of the following improvement terms is considered revolutionary in nature, being very aggressive, such as re-engineering is what usually the correct answer here. And there it is, re-engineering and breakthrough achievement. So I can already tell you that's the most aggressive. Once in a while the DMAIC model or Six Sigma makes it in there. But Kaizen, Poka-yoke, remember Kaizen is slow incremental improvement over time. Very important to companies, but not overly aggressive. Poka-yoke is kind of often used for Kaizen. So it's not A. Kanban and mistake proofing. No, those are all good, but they're not revolutionary. Containment and corrective action, no. Revolutionary in nature is re-engineering and breakthrough achievement, no doubt. Here we are at question 9. Finding the root cause of a nonconformity and applying a remedy, then verifying the effectiveness is. Wow, they went through the whole process. Preventative action? No, because preventative action, you fix it before it happens. This is the result of a nonconformity, so it's going to be corrective action. Remember, corrective action, you're fixing something that already broke. Preventive action, you're fixing something before it breaks. So we like preventative action better. We'd rather fix it before it causes problems, but this question definitely aligns with corrective action. Disposition, notification, no, it's B. All right, congratulations, you're about finished with that lecture. Hopefully you learned something new there that will help you in your ASQ certification exam. If you have any questions, ask me. As you can see, I have a lot of experience at passing ASQ certification exams. If you have any questions, please contact me through my website at alphatc.com. Go to the Contact Us, send me a message, and I'll get back with you as soon as possible. Thank you, and have a great day. Goodbye.